Simulating the way fluid flows over an aerodynamic surface requires translating continuous physical behavior into a discrete, calculable mesh. This translation is driven by the mathematical engine of weighted residual methods. These methods work by taking an approximate solution and minimizing its mathematical error, or residue, across a specific physical domain. In its generic form, we integrate the residue, r of x, multiplied by a secondary function, w sub j, forcing the total sum across the domain to 0. That w sub j term serves as the weighting function. Historically, selecting this weighting function was a subjective choice left to the mathematician. The only requirement was that the chosen set of functions had to be linearly independent. This lack of a standard meant every unique problem required a new set of custom functions, adding significant manual friction to the setup of a simulation. The Galerkin method provides a specific rule to standardize this process. To begin any simulation, we first define a set of trial basis functions, psi sub j, to build our initial approximate solution. Galerkin proposed using these exact same trial functions as the weighting functions. This duplicates the proposed solution functions, using them to overwrite the weight term entirely. Duplicating complex functions in this way complicates the integration, as we are now squaring the terms within the calculus. Why choose identical functions if it makes the resulting integral more difficult to solve? This duplication is the mechanism that allows us to relax the system's overall constraints and unlock faster computational solve times. We can clearly see the physical effect of this mathematical choice by modeling a heavy mechanical pillar under severe compression. This physical stress is described by the one-dimensional bar equation. Here, EA is structural stiffness, U double prime is the displacement's second derivative, and F of x is the distributed force. On the right, we define our approximate solution, unknown coefficients multiplied by trial functions. To solve for the unknowns, we substitute this approximate solution into the governing equation. Because it is an approximation, this substitution generates a non-zero residue. Now we apply the Galerkin postulate to this residue. We integrate the residue multiplied by our weight, psi sub j, over the domain, repeating the operation n times to account for every unknown. This repeated integration transforms the continuous physical equation into a discrete system. This system is organized into a stiffness matrix. If we look at a single cell within this matrix, k sub ij, we see the integral of psi sub j multiplied by the second derivative of psi sub I. This internal term reveals a specific requirement for the functions we choose. The function psi sub j is multiplying the second derivative of the trial function, psi sub I. This second derivative requires our trial functions to be twice differentiable, creating a rigid mathematical constraint that is often difficult to satisfy. To make the system more flexible, we need a way to reduce this differentiability requirement. We can do this by applying integration by parts. The goal is to use this calculus technique to shift the derivative burden away from the trial function. During the operation, one derivative moves across the integral, detaching from psi sub I and attaching to psi sub j. The required differentiation on psi sub I is reduced by 1 degree, and to keep the equation balanced, psi sub j increases by 1 degree. This shift creates a boundary term as a byproduct. We evaluate this boundary term at the absolute edges of the domain, from x equals 0 to x equals L. We check these against the physical conditions of the bar, where displacement is 0. In this case, these boundary conditions cause the entire term to drop out. With the boundary term gone, only the transformed integral remains. The equation now calculates the first derivative of psi sub j multiplied by the first derivative of psi sub I. By transferring the mathematical burden through integration by parts, we have reached the weak form of the equation. Transforming the equation into this weak form provides two distinct advantages for computational simulation. Compare the matrix cell before integration by parts on the left with the version after on the right. On the left, the highest required derivative is the second derivative. On the right, it has been reduced to the first derivative. This is the principle of relaxed admissibility. Because the requirement is lower, our trial functions only need to be differentiable once, not twice. This allows engineers to use a broader library of simple, efficient functions to model complex geometries. Next, consider the internal structure of the new weak form integral. If we swap the positions of the I and j indices, the calculation remains the same. Since both terms are now identical first derivatives, swapping them doesn't change the mathematical output. This creates structural symmetry across the entire system. Because the matrix is symmetric, the computer only needs to store and calculate roughly half of the data, significantly reducing memory allocation. This structure also allows the use of optimized algorithms that solve these systems roughly twice as fast as non-symmetric solvers. The Galerkin method uses function duplication and integration by parts to transform rigid equations into the efficient structural framework powering modern finite element analysis.